Welcome to Anatomy Physiology Chapter 16. We're going to talk about the organs that are involved with your senses, so your eyes, your ears. And here's a kind of an interesting thing. You can watch it if you have the proper TV channels, but they put some of them on YouTube. It's called Brain Games. And I highly recommend you to watch these various episodes. For example, you're looking at this and you say, well, which one is lighter and which one is darker? Well, they're exactly the same color. And you say, well, no, that can't be. But because this one is against a darker background and this is against a lighter background, your brain perceives it as two different colors instead of just one. If you pause the video and put your fingers up, you're going to see that they are the same color. If you want to watch it yourself, here's the link. I put it on this slide. So, sensory deprivation, this is one of the things that they thought, well, what would happen if you put somebody into warm water? They're naked, so they have nothing touching them. They're floating in the water. There's no sound. There's no light. They're just sealed in. And what happens is they start hallucinating. If you're not getting sensory information, your mind will just make some up for you. In the past several chapters, we've talked about reflexes and nerves and things that cause us to change our blood pressure, to maintain homeostasis of our body temperature, and even to do muscle tension so you don't overextend your muscles. We're going to talk about sensory receptors. How do your senses understand things? How do they get information? It might be heat, it might be light, it might be pressure, it could be a chemical thing. We have just nerve endings that are one type of sensory receptors, and then we have whole organs like hearing and sight. And a lot of our senses do transduction. So you take one form of energy and you convert it to another. You have the mechanical vibration of your eardrum when sound enters your external auditory meatus and gets to the tympanic membrane. And that mechanical moves through bone and then is converted into electrical impulses that travel back into the brain to be processed. Light enters your eyes in electromagnetic sine waves. It hits your retina, and the message then goes into the brain to be processed as electrical energy. The majority of the stimulus that comes in and stimulates our receptors never makes it up to the brain. We filter it out in the brainstem so we don't have information overload. You're not trying to process too much information. And I think I mentioned before, there is a theory that autistic people, some people think that they're shut down. And in fact, a lot of people feel it's the opposite. They're getting so much input coming in and they can't filter it all and it overwhelms them. So it appears that they've shut down. And we've said this before, but a lot of the sensations that you get don't require conscious awareness. For example, body temperature. You may start shivering before you realize, oh, I'm cold. So your body already knew about it and was taking action to raise your body temperature before you even realized that you were cold. And unfortunately, some people don't realize that they're overexerting themselves and they end up having a heat stroke because their temperature goes too high. They kind of categorize the information you get through receptors into 4 different kinds. And one of them is the modality, or what mode. how are you getting the information? Are you doing it with your eyes, with your ears, with your tongue? So that would be the modality. And this is kind of interesting. There is a condition called synesthesia, and in synesthesia, it's a hard word to say, your brain isn't wired correctly, and so you hear colors and you smell sounds because your brain is wired strangely. So here it says, hypothetically, if we could rewire the brain so signals from the ear were routed to the visual cortex, we would perceive sound or acoustical signals as light rather than sound. But unfortunately, some people actually do have that. And then there are some recreational drugs that can cause you to have synesthesia. For those who want to know a little bit more about it, you can always go to Wikipedia. In lab, we looked at 2-point discrimination, and a second property of receptors is the location. So where are you receiving the stimulus? Now, if it was heat, it would be all over your body. But in the case of someone touching you on the shoulder, then it's located just on your shoulder. So the receptive field is the area where you're getting the stimulation. So in your fingertips, you have a lot more nerve endings. So you're going to have much more discrimination. You're going to have more receptive fields. Here's an artist representation of the 2-point discrimination test. So if you put a pointed object, they're not sticking this down into the skin, they're lightly touching the skin. And they're asking the person, do you feel 1 tip or 2 tips? And you don't have as many receptors out here. So you're going to think, well, maybe that's just 1 tip because the information is going through 1 nerve. But in your fingertip, where you have so many nerve endings, then you're going to be more easily able to discriminate that, yes, here is 1 thing touching here, stimulating that nerve. Here's 1 thing touching here and stimulating that nerve. A third of the 4 kinds of information that you're going to get from receptors is the strength of the stimulus. Did somebody just pat you on the back and say, well done? Or did they slap you on the back because they were angry that you beat them? So we have the ability to say how much information we're getting. If you're out driving and the sun is too bright, obviously you're getting way too much information in the back of your eye, in the retina. So you're going to have to put your sunglasses on or you're going to have to squint. And every time you go in and you say, well, I have this pain, then the doctor or the nurse or whoever you're talking to is going to say, well, let's rate it on a scale of 1 to 5 or 1 to 10. And then you also have to rate it, is it a sharp pain? Is it a dull pain? Is it aching pain, a throbbing pain? Does it come and go? Is it continuous? We learned about recruitment in one of our lessons, and that's where you get more and more nerves to fire, or in the case of a muscle, more and more muscle fibers to contract. So recruitment or getting more neurons to fire is going to give you a stronger overall stimulus. And how fast they fire. There's only a certain speed that they can fire because you have to have the refractory period and you have to depolarize, repolarize. And the 4th is duration. How long does the stimulation last? So in the case of cutaneous pressure, for example, whenever you take a shower and then you slide in between clean, crisp sheets, that feeling is so overpowering. And then a second later, you don't even feel it. but that very first initial feeling is so nice. And when you walk into a place, the smell can overwhelm you. It can be wonderful and make you so hungry, or it can be horrible and you think, oh, I've got to get out of here. Or I remember I had a grandmother who died way too young, and so I was very young when she passed. But I remember her soap smell. And so whenever I smell that particular scent of soap, my grandmother's right there. And it's so strong, so amazing. Some of the senses you fatigue. You just stop noticing them. So if you stop the video right now and just listen, you may hear your heater running or your air conditioner running. And it was always running, and you heard it when it kicked on, but you don't pay any attention to it. For a time, I got samples from the autopsy room to determine time of death studies. And when you walk in at first, the smell overwhelms you. It is so incredible. And then after you've been there for a few minutes, you realize that you aren't smelling it anymore. So luckily for that, pay attention to these two types of receptors. The phasic receptors, I remember this because they say, oh, she's just going through a phase. She'll pass out of it fairly soon. And tonic receptors, these are the ones that are going to adapt very slowly. So this is good. For example, body position. I don't need a flash where it says, okay, you're sitting upright. I need it to continue on saying, okay, you are sitting upright and you're going to continue sitting upright. So we just categorize receptors by the information, modality, what mode, how do you get the information, the location in the brain, the intensity, and how long it's going to continue that you're receiving the information and understanding it before you fatigue or you just ignore it. Another way of looking at stimulus is what causes it to be stimulated. So thermoreceptors detect heat or cold. Photoreceptors get the photons of light from the electromagnetic spectrum that enter your eye and hit your retina. And I put this one in red. Nociceptors, this one, a lot of people say, oh man, I wish I didn't have pain. I need pain medication. Pain tells your body that something needs fixing. And so a lot of people take painkillers and it slows down the healing process. Just like when you're running a fever, a lot of people say, oh my goodness, I have to get this fever down. I have to take something. And there's a reason that your body's running a fever. And there's a reason that your body is telling you that there's pain. So it activates a whole cascade of events that'll help fix whatever it is that's hurt, whatever injury is going on. Then you have chemical receptors, and this would be your smelling and your tasting and your body fluid composition. So you actually have places in your body that determine how much salt you have. And so maybe you need to pee out some salt because you've got too much salt. Or maybe you have too much sugar. And instead of absorbing all the sugar into the cells by endocytosis and other processes, you just pee it out. And then we say, oh, that person has the sugar. That's the way they say it in my neck of the wood. Say, oh, honey, I got me the sugar. And what they're saying is they have diabetes. So the body fluid composition, you have receptors that monitor that so you can maintain homeostasis. And then mechanoreceptors, you physically deform them. So I was talking about the vibration of the eardrum. So it changes back and forth and back and forth. And I've put a little video called Ossicles, and you really should watch the little video. It shows, they put a camera inside the ear, and you can actually see the eardrum vibrating, and you can see the bones moving. So we'll talk more about the ear in just a minute. And if someone touches you versus deep pressure, so we talked about the Pacinian corpuscles and the Meissner's corpuscle. So you have light touch versus deep touch, that something's putting pressure on you. And then we talked about stretching so that you don't overstretch and tear the tendons and rip the muscles. And we're going to find out that your sense of balance has a lot to do with these little rocks called otoliths that sit on the hairs inside of your ear. When we think about our senses, we think about things that come in from the outside. But you also have a lot of receptors inside your body that are maintaining homeostasis. And then proprioception, or proprioceptors, which do proprioception, this tells you where your body is in space. So it tells you, well, I'm sitting up or I'm laying down. And if you, for example, have a few beers or a little bit of liquor, and then the policeman pulls you over and says, well, let's see you walk this line. Because you don't know where your legs are anymore, you think you do, but you're telling your leg, okay, put this leg right there, and that's not straight in front of you. But in your mind it is, because you're impaired. So proprioception, you should be able to reach up and touch your nose. But again, if you're impaired or if you've been injured, then you're going to have trouble. So they tell you to put your finger on your nose, and you may end up putting it on your cheek because you just missed your nose altogether. We have general senses throughout our body. Somaesthetic means, soma means body. So somaesthetic senses throughout your body. And then you have your special senses. So that would be hearing, vision, balance, taste, and smell. Your general senses, the ones that are throughout your body, are relatively simple. You don't need a whole lot of them. There may be only one, or there may just be a small number of sensory nerve fibers and a little bit of connective tissue holding the area together. Your unencapsulated nerve endings don't have a wrapping around it. They don't have connective tissue. So these are free nerve endings, pain, temperature. You have them in your skin, you have them in your mucous membrane. And then you have tactile disc. And we'll look at the Pacinian corpuscle. The author of this book and I disagree from time to time. And here's one of the things we disagree on. He is saying that the erector pili that causes your hairs to stand upright and causes you to have a goosebump is just a holdover from when we used to be really hairy. So if you look at the old Neanderthals, they have a lot more hair than we have now. So he says, so they serve no purpose. And then the coil, the hair receptor, the coil around the hair follicle that monitors the movement of hair, why do we still have it? Why does it persist if it has no function? I put this picture in because the Merkel cell is, as you see, where the epidermis and the dermis meet and extends up into the dermis, up into the epidermis. When you study the skin, they say, well, there's no blood vessels in the epidermis and there's no nerves. But you do have this Merkel cell that is a sensory organ. And if you remember when we talked about cells in the skin, the epidermis, there is a place right here where you have the papilla or the nipple-shaped projections, which make up your fingerprints. And this is where the dermis and the epidermis meet. And right up in these papilla, we have Meissner's corpuscles. So here's one right here. Here's your papilla, right there. So there's your Meissner's corpuscle. And then this is a blow-up of it, so you can see it even in more detail. Since this is right underneath the epidermis, and since the epidermis is so very, very thin, you can stimulate this with just a light touch. And then if you go deep down, so there's your epidermis, and here's your dermis. Right before you get to the hypodermis, here's the fat of the hypodermis, you get into the Pacinian corpuscles. And these are like a disc. It almost looks like you've cut an onion open. And so this is for deeper pressure. And then you have encapsulated nerve endings. So you've got something covering the end of the nerve, which is going to change the sensitivity of it. Make it more sensitive, make it less sensitive. You can have glial cells. You can have connective tissue that are encapsulating it. And then of these encapsulated ones, you have the light touch. You have tactile. You have heavy touch, pressure, detection of your movement of your joints, detection of your skin stretching, your tendons stretching. You have deep pressure, tickle, vibration. And if you remember when we did the skeletal system, there's a connective tissue that's around the bone, the outside of the bone. So there's a membrane surrounding the bone. And that's the periosteum around the bone. So here are little cartoon pictures showing you the various types of receptors. So here are free nerve endings, just sticking up in there, like that. And then you have the Merkel disc, or the Merkel cell. You have the one that's wrapped around the hair. You have Meissner's corpuscles that stick up in the papilla. The muscle spindle that tells you that you're stretching the muscle too much. The tendon organ, you're stretching the tendon too much. So we're still talking about your general senses. We haven't gotten into the special senses like hearing and sight. And when you're getting the information, if it's coming from the body, it's going to go into the dorsal horn of the spinal cord. This book calls it the posterior horn, but most books call it the dorsal horn of the spinal cord. But as long as you know you're going to the back of the spinal cord and entering there with spinal nerves, or if it's some information in the head, then it will go in through a cranial nerve. So we learned our 12 cranial nerves, and if you've forgotten them, go back and review them. Especially my favorite, number 5, the trigeminal, and number 10, which is the vagus nerve, which is super important since it does smooth muscles throughout the body. And some of these, like the touch, pressure, and proprioception fibers, are large, they are fast, and they're myelinated. So the bigger you are, the more signal you can send. Kind of makes sense, like a little bitty garden hose versus the great big hose that the fireman uses. It's fast, so we have some slow and we have some fast, but anytime you're adding myelin, you're going to speed up the depolarization because you're going to have that saltatory conduction. Heat and cold fibers are small and unmyelinated. One of the things that's kind of interesting is referred pain. So you may be having a pain in one area, but in your mind, you're thinking that it's somewhere else and you're complaining about pain over here when the pain actually is originating from another place. So that's a thing, referred pain. And then remember that in a lot of these neurons, they go to the opposite side of the spinal cord. So if you hurt the left side of you, you may be getting the information to the right side. So it decussates to the opposite side of the spinal cord, or the medulla, or the pons. So it goes to the opposite side. In this book, they take pain and they divide it into two different types. So one type is where you've injured your tissue. And so that's nociception. And then neuropathic pain is where you've actually injured the nerves or the spinal cord or the meninges or the brain itself. But now remember, the brain itself doesn't feel pain, it understands pain. But the meninges around the brain can feel, and the blood vessels can feel. But the brain cells themselves don't feel pain. Pay attention to this. Those of you who are diabetic, and you think, well, just one donut's not going to hurt me. Well, it depends on how out of control your diabetes is. Because one of the things that happens if you don't control your diabetes is you get diabetic neuropathy and you lose sensation. You usually get warning. It's not like one day you wake up and you can't feel your toes anymore. It usually starts out with a tingling, kind of a little bit like if you've ever laid on your arm or something and it goes to sleep and you wake up and you get that tingling feeling. People with neuropathy will have that tingling feeling, and then the nerves die. So take care of yourself if you have the sugar, if you have diabetes. Why do you have pain? I told you you're going to have pathways of chemicals that will come in and fix whatever's broken. But also it leads you to evasive action. So you're going to quit doing whatever it is that you're doing that's hurting you, that's causing you pain. Now, unfortunately, one of the things you do if you start hurting in a joint or a muscle is you favor that side. You baby it. You try to stay off of it. And by doing so, you actually end up damaging someplace else by your protective action. One of the things that older people do is they sit around and talk about their ailments and their pains and their aches. We always call it giving an organ recital. So you talk about which organs don't work as well anymore. But one of the things that they talk about is going to a physical therapist, and they go, well, I don't know why in the world they're working over on that side of me when the pain's on the other side of me. It just doesn't make any sense to me. And so then I try to explain about referred pain and protecting. So you end up hurting one side so that you don't hurt the side that hurts, if that makes any sense at all. We talked about what your viscera is in another chapter, but I'll bring it up again here because in case you weren't watching that particular episode. So your viscera is your organs that are inside your abdomen and your thorax. So anything that's in your middle body or your core, those would be your viscera. Usually when you talk about viscera, you think about your intestines. So you can have visceral pain, and it comes from one of your organs, but which one? It's hard to locate it. Now, if it's appendicitis, it's not that hard because they know about where your appendix is, and they can reach in and poke you right there on your right side and say, does it hurt here? and you about jump off the table. And you say, yes. And they go, okay, so you have appendicitis. So that one's not hard to locate. But if you have just a feeling of cramping, the pain actually makes you sick at your stomach. So it could be caused by an overfilled stomach. So if you eat too much, it kind of makes you sick at your stomach. If you need to pee and you can't pee, it actually causes discomfort. And if you have chemical irritation, my favorite is people who go to Mexican restaurants and they eat the hot sauce, and then they start having all sorts of intestinal problems and diarrhea and things. So this would be a chemical irritation. Acid reflux, this is where the stomach acid comes up into your esophagus, and this is not a good thing. This can cause you to have esophageal cancer. So you need to, if you have acid reflux, you need to have it looked at, treated. You may need surgery to push the stomach back down through the hole in the diaphragm so it can't come up through that hole. Another thing that you wouldn't really think would hurt is if you shut off the blood flow to an area. It's called ischemia. So, like a heart attack is apparently incredibly painful. And you see somebody who's having one and they'll grab their shoulder or they'll grab their arm. But women tend not to have the same symptoms as a man. So when you get into the section on heart, then hopefully we'll go over the difference in a woman's heart attack versus a man's heart attack. But ischemia is where you don't have enough blood flow to an area, and it actually hurts to shut off the blood flow. And I guess, again, I remind you of when you shut off the blood flow by sleeping funny, and then you wake up and the feeling comes back into your arm or your leg or whatever it was you slept on funny. So that'll give you just a little sample of what it might feel like. You could have pain of your bones, your joints, your muscles. Anybody who had PE and that first day where they make you exercise for an hour and then the next day you hurt so badly you can barely move because you've got lactic acid built up. People get arthritis in their joints. Of course, if you sprain your ankle or you break a bone, all of these things can cause what we call deep pain. And then you have superficial pain. So this would be on your skin. You get a sunburn, a mosquito bit you, you cut yourself when you're trying to cut your bagel open. I'm not going to ask you about the different types of fibers, but you should know that there are sharp stabbing pains versus longer lasting, dull, aching pain. So the sharp stabbing would be fast pain, and the ones that are slow pain is just the dull ache. When you injure a tissue, it's going to release chemicals, and these chemicals are going to start that cascade of healing events. And here's just, if you want to just impress people at a bar or whatever, you can say the most potent pain stimulus is bradykinin. So if you've got some bradykinin being released by injured tissue, you're going to be experiencing excruciating pain. It makes you aware of your injury, and it starts the healing process. So it brings things in. Other things that will stimulate pain is histamine. So a lot of times in pain relievers, they'll put an antihistamine in there to help relieve your misery. Prostaglandins, these are bad actors as far as causing pain, but they're necessary to get this whole healing cascade going. And we always think about serotonin as the happy neurotransmitter. That's the one that makes you feel so happy. And here they're saying, serotonin can also be a nociceptor stimulus. So it can cause pain. I guess that's kind of like love. If you haven't heard Bette Midler sing The Rose, love leaves your heart to bleed. When we did the cranial nerves, we talked about 5, which is the trigeminal nerve, and how it can cause pain in your face, and then the facial nerve. So tic douloureux can be caused by cranial nerve 5, Bell's palsy by cranial nerve 7, the facial nerve, and I told you number 10, y'all should remember that because it's vagus. So that would be your viscera. So when we talked about visceral pain, you need to get the information going through there. This is interesting, but this is more for a neuroanatomy course. It's going into a lot more depth than we actually need to go into. But the spine up to the thalamus would be carrying most of your body pain signals. And if you go into the spine up into the reticular area of the brain, that's where you're going to get your emotional and behavioral reactions, because you're going into the limbic system and on through the hypothalamus. And then the third ascending track is the one for, like, if you have a stomach ache or you're passing a kidney stone. So this carries signals up to the thalamus for visceral pain. Here's an overview of some of the stuff we've been talking about. So here's somebody that puts their finger on a thumbtack and it triggers the nerve ending, a pain receptor, nociceptor, in through there, and it's going to go over and it's going to synapse in the back, the posterior or the dorsal horn back there, and synapse and go on up and be processed. Here's a breakdown explaining why you would feel a heart attack as in your shoulder or your arm. So you have converging neural pathways and the brain doesn't know where the pain's coming from. So the brain can't distinguish the source. So the heart pain is felt in the shoulder or arm because both send pain input to the spinal cord segments from T1 to T5. So again, that's more information probably than you need, but you should know about referred pain because you think it hurts one place, but it's actually somewhere else. I think this picture is funny. So here's pain coming from your heart, and here's pain coming from your shoulder, and the brain is like, gee, I don't know which one it is. I've had a number of friends who were heavy smokers, and they suddenly have a sharp pain in their lower back, and it radiates out over their hips, and they walk around and go, man, I didn't do anything to hurt myself. And I'll just say, well, you might want to go in and have a lung x-ray. And a lot of times they come back and said, how'd you know I had lung cancer? I said, well, because one of the first places it seems to feel, to be detected, is in the lower back. So if you know a smoker who's starting to have back pain, you might tell them to go and have their lungs checked. So here's just a picture. Your appendix, like I said, you're going to feel that in your right side. And if they touch it, you're going to know it's your appendix. So that one is not really referred all that far away. But some of the others, like your heart, referred down to your lung. And imagine your lung problems being felt in your diaphragm up in your neck. So there's your referred pain map right there. Many people are surprised to find that they have the ability to make opium-like substances in their body. And they act as neuromodulators that will block pain and also give pleasure. And enkephalins, endorphins, and endorphins are three of them. Enkephalins are 200 times the potency of morphine. So, of course, my question is then, why don't we extract this? Why don't we make this in the laboratory and give it instead of morphine? Imagine, and this is natural because you normally make this, whereas morphine is an extract, and it just is a coincidence that we actually have a receptor in our body that accepts morphine, because it's not something you would normally find in your body. So why would you have a receptor for something that's not normally in your body? But enkephalins. So I talked, when we were doing muscles, I talked about runner's high. And if you're running to the point where you're in pain, and then these kick in, you get that pleasure. I know that sounds really odd, but that's what the runner's high is. If you run, you exercise past the point of pain, then all of a sudden you start feeling good. And that's what's happening. And unfortunately, as you're feeling this pain and then you're feeling this pleasure, you forget to eat. So you'd rather run, you'd rather exercise than you would to eat. And you have to eat because you have to maintain the muscles, you have to maintain the energy, the ATP, and all of that stuff. So a lot of people who exercise too much end up dying. And that sounds so odd. But a friend of mine rode his bicycle all the time, up and down mountains, just because he could. And he was skinny as a rail, and everybody goes, oh my goodness, he's so physically fit, there's not an ounce of fat on him. And he just died. Did you ever wonder, when you're in pain, a lot of times you rub the area that's hurting you. Stop and think about it. You get a headache and you start rubbing your temples, rubbing around your eyes. You get a bee sting and you start rubbing the area. You pull the stinger out and you start rubbing the area. So if you rub or massage an injury, the mechanoreceptors can activate inhibitory spinal interneurons. And if you activate the inhibitory spinal interneurons, they can release those enkephalins, those wonderful, stronger than morphine pain relievers and pleasure receptor givers. So if you're feeling pain, if you're stimulating a nociceptor receptor, you're going to send the message up the spine to the thalamus. So they call it the spinothalamic tract. And once it gets to the thalamus is going to send the signal to the cerebral cortex. That's the thinking part of your brain. So that you understand the pain. You're aware of the pain. Supposedly, if you can distract the brain so that it's not thinking about the pain will go away. So I've heard of cases where people could think away pain so well that they could actually perform surgery on them without any anesthesia. So I'm not one of those people. I want to be put to sleep. In order to block the pain, then you're going to send a message down. You're going to use serotonin secreting analgesic fibers. So we've talked about acetylcholine, we've talked about norepinephrine, and now we're going to talk about serotonin. So again, we think about serotonin as the neurotransmitter that makes you feel happy, but it also will talk to the spinal cord. It'll go to the dorsal horn or the posterior horn. Once you get the message with the serotonin into the posterior horn or the dorsal horn, then those descending analgesic fibers synapse on those inner neurons, and those inner neurons have the ability to secrete enkephalins. If you can block some of the things that cause pain, like substance P, then that's going to stop the pain too. So here it is, putting the whole thing together, and you put your finger in a flame, so you're burning your finger. Before you were putting your finger on a tack, and now you're going to get the message all the way up, and once you get up to the cerebral cortex and you think about it, then it's going to send the message down. You're going to get to the posterior, which is the dorsal horn of the spinal cord, and it's going to release that pain relieving enkephalins. So now we're going to switch over and we're going to talk about taste and smell receptors and how do we stimulate those. I remember I always felt cheated when I learned the information on this slide. It's like, no, they taught me wrong. So all those little bumps on your tongue, you go, those are taste buds. And then you get into anatomy class and they go, well, no, they're not. They're actually lingual papilla, which are the visible bumps on your tongue. And the taste buds are beneath and are not visible to the eye. I'm like, what? Now, one of the things that I've noticed, especially I have grandchildren, is they are picky eaters. Oh my goodness. And I remember what a picky eater I was. And now I enjoy things that as a child I wouldn't eat. So the taste buds, whether they're under the lingual papilla, kids have other tasting buds inside their cheeks, on their soft palate, in their throat, and even down to the epiglottis, which is the flap that we're going to learn about that's over your vocal cords. It's like, wow. So to them, maybe this taste is too strong. I remember I hated onions as a child. And if you made me eat onions, I would actually throw up. And now that I'm older, oh my goodness, fry me up a mess of onions and throw them on my hamburger, and I'm just as happy as I can be. I'm not worried. If you want to learn the 4 different shapes of the lingual papilla, you go right ahead. I'll not be asking you about that one. But you have these different ones that have different functions in helping you analyze what it is you're eating. Another thing, you know, when you've believed something all of your life and then somebody goes, well, no, actually, that's not right. And you're like, are you kidding me? I've believed that my whole life. So one of the things that they do, and one of the labs they do in a lot of universities, is they have you map your tongue. So they've got little droppers, and they drop a little bit of something on your tongue, on the end of your tongue, and you say, does this taste sweet, salty, or bitter? And now they're saying, no, that doesn't really happen. You can't map your tongue. That's just a thing. Like, no. One of the biggest mysteries that they've come across with COVID is one of the biggest symptoms that kind of makes you sure that you had COVID is you lose your taste or your sense of taste. And your sense of smell and your sense of taste are linked. We replace our taste cells every 7 to 10 days. So it seems like after you got over COVID, within a week or so, you get your sense of taste back. But I've talked to too many people who had COVID, and either they can't taste and everything tastes like cardboard. One person said everything tastes like burnt rubber. I thought, oh my gosh, that's horrible. And then another one said that the sense of taste had come back, but like strawberries tasted like something completely different. So they remembered what strawberries tasted like, but that's not what they taste like now after, post COVID. So that's kind of an interesting phenomenon that I haven't heard anybody be able to explain yet. Here's a picture of your tongue showing you all the different shapes of those lingual papilla, not taste buds, that you have. You have all different kinds. Well, you have 4 different kinds. And here's an electron micrograph picture of someone's tongue. Kind of cool. So papilla means nipple shaped. And back when we were mapping the tongue, we did salty and sweet and sour and bitter. And now they've added a 5th taste, umami, which is a meaty taste of amino acids in chicken or beef broth. And how about that one? One of my favorite foods is Japanese food, Chinese food. And if you go into a lot of Chinese restaurants, they'll have a sign up or they'll have something on their menu saying which things have monosodium glutamate in them. And that the 5th sense of taste, the umami, is partly caused by glutamates. That might be why so many people love Chinese takeout. And you actually love the taste of fat. So one of the things that they came up with, I know Lay's potato chips and Doritos had it for sure. They put a very large fat that they cooked. So when you ate the potato chips or you ate the Doritos, you got that wonderful, wonderful greasy flavor that you really love. But the fat was so large that it couldn't be absorbed by the small intestines. So they could truly say that it was fat-free because no fat would stay in your body. It would pass out with your fecal mass. But what they weren't counting on is people who really like their Doritos or really like their potato chips will eat a whole lot of them. And so you end up coating your intestines with these really large molecules of fat that you can't absorb into the body. So you don't get any nutritive value and you don't get fat from eating the fat. But it also greased your fecal mass. So people ended up having diarrhea, or they would end up having anal leakage. That was on the package. It said may cause anal leakage. So the fat would just run out through the anal sphincter into your underwear. So they took that off the market, but it was too bad because I really liked eating those. And you could tell that the ones that had the large fat in it because they would put wow on the package. So you go look for the wow section. I think that little kids have more of the detectors for food texture. They've got those receptors. Also, a lot of people don't like food that's cold. So it's got to be warmed up or they won't eat it. Now, by the time you get to college, one of the main things you eat is cold leftover pizza because you don't care anymore. And when you eat things with hot peppers, it's stimulating your pain receptors, not the taste buds that are down in your lingual papilla. So I must have a really sensitive trigeminal nerve because I cannot eat hot things. It literally hurts my mouth so much that I can't enjoy it. And I'm always looking at people who are just grabbing jalapenos and putting ghost pepper sauce on. I'm like, oh my gosh, how in the world are you doing that? But your trigeminal nerve, remember number 5? Some things that you taste require a transmembrane protein. So we talked about first messengers and second messengers and G protein coupled receptors. So your sugars and your MSG, your glutamate, that's how you're gonna get those tastes and get the sensation of yummy to your brain. And then others like sodium and acids, like when you're drinking soda pop, it's got carbonic acid from the dissolved carbon dioxide. So those actually depolarize the cells right there. So they don't have to go and do this whole process and cause a reaction inside of the cell. They just go bam, right there, and depolarize it. And you go, salty, delicious. My students come and ask me questions from time to time when we have in-person classes. And one of them that they came up to me is they said, why is this high fructose not a good idea? And I said, I've been wondering that myself because when you think about sugar, you think about table sugar, where you go and you buy it in the grocery store in a bag. It is a double sugar. It's called sucrose. So you're getting 2 sugars. But there's an enzyme that can break the 2 sugars apart, and then you have glucose and you have fructose. Now, you know that we use glucose in IVs. It's also known as dextrose. But Americans like to call it glucose, and the rest of the world calls it dextrose. So you can divide it in half, and so now if you're making a cake or you're making something that's sweet, you can use half the sugar and get the full sugar taste. And it's natural. Glucose is natural. Fructose is natural. So we just use sucrose because it's cheap and we can get it at the grocery store and that's what's there. But we could just as easily make something with glucose and only use half as much. So if it calls for a cup of sugar, you use a half a cup of glucose and you'll get all the taste that you would have from the sucrose. Because the receptors don't differentiate between whether you have a single sugar or a double sugar, a disaccharide. So I thought, well, shoot, fructose is half, so you only have to have half as much. This is a win-win situation. You get half the calories from sugar if you use fructose. But the problem is, pretty much anywhere in your body you can use glucose, but in order to use fructose, you got to send it to the liver and switch it around so it looks more like glucose before the body can use it. And so what happens is you end up overworking the liver. So they're starting to see liver damage from high fructose foods. So I just thought I'd throw that in there because I thought it was kind of interesting. But man, too bad. Half all the flavor of sugar, all the sweetness, stimulating your neurotransmitters, stimulating the dendrites at the base of the taste cells. And if you remember when we did the cranial nerves, we talked about the ones that are involved with taste. Well, glossopharyngeal, that just tells you right there, glosso means tongue. So you're pretty much knowing that one's going to be tongue. And then your facial nerve is the anterior. So remember, anterior is the front. That's the part you stick out at people. So the anterior 2/3 of the tongue, the information is carried by the facial nerve. And then the glossopharyngeal nerve is the back third. And then the vagus nerve is this would be your kids mostly, because remember the kids have more taste buds than we do. So they have them in the palate, the pharynx, and the epiglottis. So they're using their vagus nerve also. Now, one of the things that I thought would be interesting is if somebody was doing a science fair project and they were taking these people who had lost their sense of taste due to COVID and do the taste test on them. You know, put a little sugar in the front of their mouth, put a little sugar in the back of their mouth, put a little of the umami in the front and in the back, the sweet, sour, and bitter in the front and the back, and see, is it something to do with one of the cranial nerves that's causing the people to taste things peculiarly? So I just thought, man, what a cool and timely science fair project that would be. You have the autonomic reflexes that we talked about in chapter 15. We talked about salivation and gagging, vomiting, autonomic reflexes. So that's one part of tasting, because you need to salivate. You need to mix a lot of saliva with the food in order to get it down into your stomach. You're going to be surprised when we do the digestive chapter at how much spit you actually make per day. Is amazing. And we're going to learn about peristalsis. Again, we're going to talk about it, which would cause you to gag or vomit. And here is in the thalamus, you are actually sending the sense of taste. You're going to send this off to the cerebrum, and you get a combination of, here's the flavor, whether you like the taste of the flavor, and is the food visually appealing? Isn't that interesting? Does it smell good? So there's some cheeses. If you smell the cheese, you're like, oh my gosh, there is no way in this world I'm going to eat anything that smells like that. And then somebody says, well, go ahead and try a bite of it. You know, you may be surprised. And so you go, okay, and you try a bite, you go, oh my gosh, this is delicious. But good heavens, it stinks. So I'm going to pause here, and I'll start the second half of chapter 16 with our next lecture. But I'll leave you with this, that there are about 2,000 to 4,000 different odors that you can distinguish. And there are some people who have such sensitive noses, they use them to smell wines. And where some people like their hand models and they insure their hands, these people insure their olfactory sense, their sense of smell. I just thought that was so interesting. Can you imagine having that sensitive a nose?